Okay, so let's get to 15.6, which is about how to change variables more generally than the way that we did for spherical or polar or cylindrical coordinates. How does we can make, just like in one variable in calculus 1, it's basically you did u substitution. That was really a change of variables, right? We changed which variable we integrated in. And that allowed us to solve a whole bunch of integrals. Now, as you saw with, let's say, polar coordinates, it wasn't necessarily about just being able to, making the function simpler, which is all that you were interested really in calculus 1 when you were doing u substitution. You were trying to, make what's under the integral simpler so that you could find the integral. But in several variables, there's really two things. You can make what's under the integral simpler, and you can also make the region that you're integrating over simpler. And hopefully you can do both. So we saw, a lot of the examples that we saw, actually both happened. But sometimes there's a trade-off. Sometimes you can make the region simple, but you make the function ugly, or vice versa. Well, that's the way life is. But in a good case, you can make both simpler or maybe make the region simpler and not screw up the function, or maybe make the function nicer and not screw up the region too much. All right. So how does this work? Let's do it. Let's do this. General theory only in the plane. So we're going to have two sets of variables. We're going to have x, y, and we're going to have u and v. Right. So it's sort of like the u substitution. So we need two variables, so we're going to have u and v. And what we're really going to have is some function that actually goes from u and v to x and y. So g is going to be a mapping. It's going to be this. For each point u v, it will give you a point x and y. Sorry, u v. Y u v, right? So really, it's two functions, x and y. They're functions of u and v. So for each point u v, you get a point x, y. You can think of it as position vectors. It could be a vector valued function, capital G, right? Or it could be point valued, as we're doing right now. So how does this work? For example, for the polar coordinates, that g was our uv. Well, let's call them r and theta instead of u and v, and this was x was r cosine theta, and y was r sine theta. Right. So that's the way it worked for polar coordinates, and really what you want to figure out is if I have my something in the uv coordinates, some region over here, right? And let's call this, I'll be calling this D. Then in the xy coordinates, this is going to get taken to some maybe more complicated, maybe less complicated region R. And the way we maybe write that is that g of d is equal to R, right? And we really want this to be have that exactly 1 point over here goes to exactly 1 point over here. That's the kind of mappings that we'll want for this, right? We don't want the mapping to sort of squish some too many points into 1 point, or maybe sort of overlap the region onto itself too many times. You'll see where this comes up, and I'll mention this again when we write down what when it comes to the integral. You weren't really worried about that in one variable, but that's really because it sort of takes care of itself in the integral, and in several variables it's more complicated. You really want to be want to worry about this being a so-called one-to-one mapping, right? That you don't have 2 points in D going to a single point in R, or at least you don't have it too many times. Maybe if you have it on the boundary of this region, you don't worry about it too much. But inside, you don't want this to be happening. So, right. So let's, for example, figure out if I have this change of coordinates, this polar change of coordinates, right? And let's suppose that we have the UV space, or in this case in the R theta space, we have this set. I'm going to take a rectangle, right, where R is between 1 and 2, and it is not really drawn really well to scale, and theta is between pi over 2 and 3 pi over 2. Then what does that mean in terms of x and y? Well, that means that R is between 1 and 2, so the radius is really between the circles of radius 1 and radius 2, and we also have that theta should be between pi over 2 and 3 pi over 2. So pi over 2 is out here, right? And 3 pi over 2 is out here, right? You have pi over 2 pi, 3 pi over 2. So that means that this region is this half of a washer, right? This is at 1 and 2, right? So this would be my D, and this would be my R, right? And you saw that if we wanted to integrate over this, we integrate over this D, right? And you can maybe more see why we'd call this a polar rectangle, because it's a rectangle over here, right? You can also see that it is, as we said, one-to-one. There's for each point over here, it goes to exactly 1 point over here, and no other point in D goes to that point in R, right? And that's really why we, over here in polar coordinates, that's why we're always restricting theta to some interval of length 2 pi, maybe between 0 and 2 pi, or maybe between minus pi and pi. We really didn't want several different points going to 1. Now, maybe another example of, as I was saying, sometimes it's sort of okay for some points to go to a single point. So, for example, if we have this rectangle from 0 to 1, and from 0 to let's do to pi, right? This is our D. Then our R is going to be, it's going to be the upper half circle, is going to be the R, right? So G is going to take this D into this R, but you can see that this point, well, these all these points over here, right? When R is 0, but theta is anything, they all go to this one single point, right? So, but as I said, this is on the boundary. It's not going to worry us too much. This for any point inside this rectangle. If I look at its image, there is no other point in D that goes to that same point, right? All right. So that's that's the example of polar coordinates. Maybe another useful example is linear maps. So this is when we have something like g of uv is when x is au plus bv, and y is cu plus dv. Now this is had some linear algebra. This is the linear map corresponding to the matrix A, B, C, D. Right? That's this linear map over here, right? So now we can figure out where this goes, right? We've seen this before, actually, right? So it's let's just figure out where this takes some square. Let's suppose the unit square, right? So if I have uv and the unit square, that's the square of what I mean is the square is side 1, right? So this is my d, right? And let's see where that goes. Well, 0 goes to 0, right? Because if I the 0, 0 point, 0, 0, 0, 0, I just get 0, right? So this point goes all the way to here, right? What about this point? This is where u is 1, and v is 0, right? Well, that's the point. I'm going to draw sort of a fake one, right? I don't know what A, B, C, and D are, so I can't really draw exactly what it is, but this is going to be the point AC, right? So maybe it's over here, AC, right? Now, this point over here goes to the point BD, right? So maybe that point is over here, BD, right? This guy over here, well, it goes to, sorry, it sort of doesn't look quite like this looks better. This is A plus B, C plus D, right? Because this is the point 1, 1, right? So this is my R, right? As we've seen these sort of pictures before, right? So a linear map is always going to take a rectangle into some parallelepiped. So, all right. So that's how we, that's for a linear map. Now, what about maybe more complicated? Then you have to think a little more. Let's do an example of this. Let's suppose our map is this, and this really isn't actually about this. It's taken completely out of context. This is a map that does get used often. It's a square of a complex variable, if you know what that is. But anyway, let's not worry about that. So let's just look at this map and see where it takes. Let's again take the unit square. So we have 0, 1, 0, 1, and then 1, 1 here, right? And this is our D. Let's see where does it go. So this is X, Y. Well, let's start plugging in 0, 0. Where does it go? Well, if I plug in 0, 0, right, G of 0, 0 is, well, 0, 0, right? So this point goes to here. What about the point? Well, let's maybe instead of going through different points, let's look at let's simplify this. Let's go over this entire line. So where does this line go? Well, this is when I'm setting V to be equal to 0, right? So I'm looking at where this goes, right? What kind of points do I get? I'm really parameterizing a curve. So if I plug in V equals 0, I just get U squared 0, right? So, and U is supposed to be between 0 and 1, right? So this means X goes between 0 and 1, right? So X goes between 0 and 1, right? It goes over here, right? This point goes over here, this point goes over here, right? Okay, how about this guy? This is when U is 1 and V is between 0 and 1, right? So we're looking at 1V, and so this is 1 minus V squared, and then when I plug in U equals 1 here, I just get 2V, right? And if you look at this, this is if I well, let me do it instead of just talking about it. So this is when you have X as 1 minus V squared and Y is 2V, right? So what I could do is I could solve for V, right, over here. So I'd have Y over 2 is equal to V. I could plug that into here, and so I get Y as 1 minus Y over 2, X is equal to 1 minus Y over 2 squared, right, or maybe 1 minus 1/4 Y squared. Well, this is this looks like except with X and Y flipped, right? It's like a graph of a parabola, right? It's an upside down parabola, right? So this looks like this if I look at this for all X and Y, it would be sort of this parabola like this. But I'm only looking for V between 0 and 1. V is well, twice V is Y, right? So I will get I will go from 0, and then I will actually go up to Y equals 2, right? And that's when X is equal to 0, right? So I'm parameterizing this bit, right? This bit of the parabola. All right. So now we do sort of a similar thing. We go on this side. So this is G of, well, this is when V is 1 and U is now between 0 and 1. So, and I will have, well, V is 1, so this is U squared minus 1 to U. And it's basically sort of, instead of upside down parabola, it's a right side up parabola. You can do sort of a similar analysis as over here, and you'll get that it's this bit right over here, right? And then finally we look at this guy. So this is when u is 0 and v is going to be between 0 and 1. And so this is, well, when u is 0, I have minus v squared 0. So it's this guy over here, right? So this is my R, right? This region right over here, right? Okay, so sometimes it can be a little tough to figure out exactly how this looks, right? But something that often works is sort of look at where the boundary goes, and if you travel along the boundary, you will travel like this around this region over here. Okay, so that's one thing for sort of general maps. It can be somewhat difficult to actually find what's the region, what's R, right? And actually for integration, well, usually sort of know the R you're trying to figure out. You're trying to make it into the image of a rectangle because we know how to integrate over rectangles. That's one of the biggest applications of this, is making the region simpler. Now, if I have a region like this, a parallelepiped, right? Then sorry, not a parallelepiped, parallelogram. If I have this parallelogram like over here, then I could write it as an image under a unit square by basically, if I know these two coordinates, right, then that gives me A, C, B, D, right? I just put them in this in this matrix, or in this guy, and I have the mapping, right? So I can, for a parallelogram, it's fairly easy to figure out the G, right? So for something like this, maybe it's much harder, right? And we have one of these for like polar coordinates. Well, we know exactly what the polar rectangles look like, so we know exactly when polar coordinates are the good coordinates, right? That's when you have pieces of circles or washers and stuff like that. So, all right. So that's trying to figure out what region goes to what region. So how do we integrate? Well, to integrate, we need to figure out how does the area change, right? Because we're integrating. What we really want to do is we want to integrate f of x, y over some region R with respect to the area, right? And so we have g that's going to take some d. Hopefully d is going to be nicer and simpler to this R, right? We're going to figure out what this g is, and we're going to want to write it as the integral over d, which is in the uv coordinates, right? So over here we're going to want to write x of uv, y of uv, but now it's not going to be dA over here, because this doesn't quite well, I guess it is in some sense the dA from over here, where this guy is. Maybe let me write it instead of dA, just so that it's clear in what variables. And this is the dA, that's the dx dy, right? And over here, I'd really want the du dv, this dA, but that's not this dA, right? And you think about how does this change, right? And there's something missing here. What's here is the same thing as in one variable, right? I mean, in one variable, if we had, what was over here was really the derivative of this. Let's suppose that there was just x and u, right? Well, there would be derivative of x here, right? But here we have both x and y, and what is here, and I'm going to say exactly what what that is in just a moment, is the absolute value of the so-called Jacobian determinant of x and y with respect to u and v. Okay, what the hell does that mean? Well, first, if we think of a linear g, what did a linear g do? So a linear g changes area by the determinant of g, right? Now, the determinant of g, well, it could be positive or negative, right? So we really take the absolute value of the determinant of g, right? Because g could flip orientation, if you remember, from a long time ago. So we take the absolute value of the determinant, right? And that tells us how does g change area. And that's really what we want over here, except g is not linear, right? But this is what it means for a function to be differentiable. It means that it's that locally it acts like a linear mapping, right? So it really should be the determinant of the linear mapping that happens to be the derivative, right? And so if we think of the matrix, what locally what this g, what the derivative of this g is going to be is well, let me just write it down. It's this matrix u x d v d y du dy d v, right? That's really the derivative of this g, right? Oops, I think I've left myself enough room. So now this so-called Jacobian determinant, well, that's just the determinant of this matrix, right? So this is the Jacobian matrix, sometimes that's what people call it, or the Jacobian derivative. That's the linear map that approximates g near any point. So that's the linearization of g, and we're taking its derivative, right? And so, well, for us, maybe what's important is just the formula. So dx du dy dv minus dx dv dy du, right? And we're taking the absolute value of this. Now here is another place where using vertical bars for determinants would just be confusing, because then you think, well, what are these vertical bars if I'd have vertical bars over here? Okay, it's better to just write determinant, det, det, right? Everybody knows what that is. Okay, so this is what I'm supposed to plug in here, right? And you know, this is exactly what you get. For example, for polar coordinates, right? We got the dx dy was r dr d theta, right? So let's see what this thing comes up to if we have the polar coordinates. So this is when our theta is our cosine theta, our sine theta, right? So what is the dx y, this Jacobian determinant, r theta, and what is this? Well, this is well, let's just compute it, right? I mean, we have this formula. So this is my x, right? So u is r. So this differential with respect to r is cosine theta, right? Times dy dv. So this differential with respect to sine. So it's derivative of sine is cosine. So r cosine theta minus now we have dx dv. So this differential with respect to with respect to theta, right? So that's derivative of cosine is minus sine, so it's minus r sine theta, right? And times dy du, u is r, so it's this thing with differentiated with respect to r, so sine theta. Well, it looks still complicated, but if you simplify this, right, this minus sine cancels out this minus sine. I really have just cosine squared, I have sine squared. I have both things multiplied by r. It is really r cosine squared theta plus sine squared theta, which is just r. Well, that's exactly what we got, right? If dx dy was r dr d theta. Now, one thing that you will notice here is, I didn't put in the absolute value signs here, but it actually comes up positive. But if I, for example, flipped the r and the theta over here, it would make this would come out to be minus r. You can double check that. That's what would happen, and that's really why we have the absolute values, right? Because the order here does take care of orientation, and as far as the integration is concerned, we don't want to worry about it. We don't want to see if the g flips orientation. We don't want to see it, right? We're just interested in the area, not in sort of a signed area. We're not worrying about, well, is it the area but oriented opposite, right? We just wanted both positive orientation on both d and r, basically. That's just like when you are integrating in one variable, from let's say on the interval from 0 to 1, you're integrating either from 0 to 1 or from 1 to 0. Well, it's both the same interval, right? But one of them you're integrating in the opposite direction, right? And that's really what we're taking care of here, right? It's easier to talk about orientation in one variable, and we don't want to talk about it here. So that's why we're putting the absolute value signs over here, right? Right. So that's what it is for polar coordinates. Well, let's do a couple of examples just so that you see how this actually works, and for something else, something not just polar coordinates, or it's the same sort of thing is done in 3 variables. So cylindrical coordinates and spherical coordinates come, it's sort of the same idea, right? So let's suppose that we want to integrate x squared plus y squared dA and R is the rhombus with vertices. I'm going to have the origin 0, 0, 1, 1, 1, minus 1, and 2, 0. Right. So let's draw R. So we have 0, 0. Let's maybe do. We have 1, 1. Right. That's this point. Then we have 1, negative 1. That's right here, right, and 2, 0. So it's this. This is R, right? This guy over here, right? Now we can, if this was the 1, 1, 1 minus 1, and 2, 0. Well, this is when we had, remember when we had a parallelogram, I could just make these those A, B, C, D guys in some order, and so for example I could pick UV to be x plus y, x minus y. All right. Now, this is if you look at sorry, UV, U plus V, U minus V. Sorry about it. So let's look at the Jacobian Jacobian determinant, right? So this is x, this is y. Well, the Jacobian determinant is really just determinant of this matrix, right? What is this matrix? This matrix is the matrix. Well, I have 1, 1, 1, minus 1. It's this guy, right? And the determinant of that is 1 times negative 1 minus 1 times 1. It's minus 2, right? So I'm going to have a minus 2, but I'm going to take absolute value, right? So what we do is we write, well, we have R, x squared plus y squared. This done with respect to x and y is so I didn't write down where the u and v, right? I didn't draw that. The d, it's the same thing that we did before. It's the unit. This is d, right? It's the unit square, right? So I can write this down immediately as an iterated integral, right? And I'm going to have x squared. So, okay, x is u plus v squared plus y squared u minus v squared, right? Now, if I have dx dy, so now over here I should have absolute value of this. So absolute value of minus 2, that's just 2 du dv, right? And so this is 0 to 1, 0 to 1. What is u plus v squared, right? I mean, it's going to be u squared plus 2 uv plus v squared, right? And what is u minus v squared? Is going to be u squared minus 2 uv plus v squared, right? And so if I add those, the inside nicely cancels out, right? And so I'm going to get 2u squared plus 2v squared. I'm going to get another 2 here, so I'm going to have 4 u squared plus v squared du dv. And now I will assume that you guys know exactly how to do these sort of iterated integrals, right? In particular, this one is an actual quite simple one. So let's look at another one. Let's look at a more or slightly more complicated one. Suppose that R is the triangle with vertices I'm going to have the origin 1, 0 and 1, 1. And let's suppose that I take my G U V, let it be in, this I guess, just like U substitution sort of comes from, how do you know what to substitute? Well, experience. This will be experience. Let me maybe draw this just so that, if I didn't draw it, I wouldn't have come up with the formula that I'm going to come up with. So it's this triangle that has these vertices, right? So 1, 0, 1, 1, 0, 0, right? So this is my R, right? The U that I'm gonna use, the D in the UV plane is just gonna be again the unit square, right? But how do I go from here to here? Well, one thing that we could do, we could say, well, X could really just be U, right? That's I can just take X to U, and then I could smush the Y by how far I am along the U U axis, right? So I could do UV over here, right? Now this is actually a very famous famous mapping. It's called a Blowup mapping, but it's not important, for this example, for this triangle. But it's this comes up quite a bit. All right, so let's just double check that it goes where it goes. Well, let's figure out where these lines go, and let's just do it. We can do it in our heads, right? This line over here, that's when V is 0. Well, it does go to this line over here, right? Over here, when U is 1. Well, when U is 1, I'm just going to 1V, right? So I'm really, it just goes to the exact same points, right? Goes over here. Now, where does this go? Well, this goes, this is where V is 1. So it's UU, right? Well, that's precisely this line, right? Right? Whatever U is, both X and Y are that U, right? And where does this go? So this is where U is 0, so just 0, 0. So all of these points actually go to the origin. Again, it's not 1 to 1, but inside it is. And so again, we're not really worried about what happens on the boundary. That's not a problem for the integral. All right. Okay, so now we have this, and let's integrate something. Let's integrate this function y e to the x squared dA, right? And well, so for this we have to figure out what is the Jacobian determinant. So x, y, u, v, right? So it's going to be dx du, dy dv, right? So dx du is 1, dy dv is u. Okay, so I'm going to have u minus dx dv. Oh, that's 0. And so whatever dy du is just 0, right? So okay, so this is just u. All right. Now u on this rectangle, on this unit circle, is just always positive, right? So I don't really need to put in the absolute values. So this is going to be the integral over the square of well, I now have to plug in. So this is going to be y is uv, right? So uv, x is u squared, d u. Oh, sorry. I forgot about this thing, right? Times u d d u dv, right? And so now we simplify this a little bit, and again, I'm not gonna compute it, but this is what it is. I'm not gonna compute it because it's a integration by parts, and I'm too lazy. So, but it's not bad, right? It's one integration by parts. So it's really going to be, maybe let me simplify it down for you, down to a calculus 1 integral. So I'm going to have 1 dv dv times the integral from 0 to 1 of u squared e to the u squared du, right? This is 1/2, so this is really just 1/2 times this integral, and I'll leave that as an exercise. All right.